Hello, my name is Andrew Cooper, and today I'm going to be showing the solution to problem 8.7b. This problem is an elementary reversible organic liquid phase reaction that's carried out in a flow reactor with a heat exchanger where A and B are consumed in equimolar parts. Required to answer this question is to plot the conversion and temperature profiles of the plug flow reactor up to a reactor volume of 10 dm cubed, with Kc equal to 10 meters cubed over kilomoles at 450 Kelvin. Our givens for this problem are as follows. HA at 273 Kelvin is negative 20 kilocalories per mole. HB at 273 is negative 15 kilocalories per mole. HC at 273 is negative 41 kilocalories per mole. The heat capacities of A and B are 15 calories per mole Kelvin, and the heat capacity of C is 30 calories per mole Kelvin. K is equal to 0.01 dm cubed per mole per second at 300 Kelvin. E, the activation energy, is equal to 10,000 calories per mole. U of A is equal to 20 calories per meter per second per Kelvin. The temperature of the coolant of the heat exchanger is 450 Kelvin. Ca initial is 0.1 kilomole per meter cubed, and Cb initial is 0.1 kilomole per meter cubed as well. The feed enters at 300 Kelvin with the velocity at 2 dm cubed per second. The temperature profile of this plug flow reactor with the heat exchanger is dT per dV equals U of A multiplied by the difference between the temperature of the coolant minus the temperature plus negative Ra times negative delta H reaction all over F A naught multiplied by the sum of theta multiplied by the specific heat capacity plus the change in specific heat capacity. The solution for this problem starts with solving delta H reaction and the change in specific heat. So to solve for the difference in the enthalpy of reaction, you take the enthalpy of the products and find the difference between that and the reactants, which is Hc minus Hb plus Ha. So the delta H reaction is then found to be negative 6 kilocalories per mole, and we convert it to 6,000 calories per mole to aid us in calculations in the future. The change in specific heat is equal to products minus reactants, as well as the change in enthalpy. So the specific heat of C is 30 calories per mole Kelvin, and it's subtracted by 15 calories per mole Kelvin plus 15 calories per mole Kelvin, which corresponds to the specific heat capacity of A and B combined. So the change in specific heat is 0 calories per mole. The next step is to look at the rate law for this elementary equation. It's defined below. The equilibrium conversion is the conversion equilibrium equal to Kc over 1 plus Kc. We then perform a stoichiometric balance where Ca is equal to the initial concentration of A times 1 minus the conversion factor. The concentration of B is equal to the concentration of A initial times 1 minus the conversion factor as well. And then the concentration of C is equal to the concentration of the initial concentration of A times the conversion factor. Okay, so this is the energy balance for a flow reactor with a heat exchanger. And if we plug in our variables of negative delta H reaction as 6,000 calories per mole, and this part of the equation at the bottom here, and solve, we end up with this final equation where dt per dv equals U of A times the difference of the coolant temperature of the heat exchanger minus the temperature plus negative Ra times 6,000 calories per mole all over Fa naught times 30. Okay, so the volumetric flow rate is solved as follows. The equation for volumetric flow rate is flow of A equals the velocity of the feed times the concentration of A initially, which is 2 dm cubed per second times 0.1 kilomoles per meter cubed. And then we convert to get it into mole per second units. So then the flow, or the volumetric flow rate, is therefore 0.2 moles per second. The rate law for this equation is negative Ra equals K concentration of A times concentration of B minus the concentration of C over Kc. If we combine that with our stoichiometric balance and we plug in the concentration of A initially times 1 minus the conversion factor into C of B, and then the conversion factor of C, or excuse me, the concentration of C, which is equal to the concentration of A initially times the conversion factor, into the rate law equation as well, we can solve into this final rate law equation, which we'll plug into polymath later. Next, we use the Arrhenius equation, and this is used to express K and the equilibrium constant. We're going to be using an R value of 1.987 calories per mole Kelvin, which is approximately equal to 2. So this is the Arrhenius equation here. And if we solve it and take the power of E to both sides, we can get rid of this natural log, creating this exponent over here on the right-hand side of the equation. And then we can get K times, or K of T2 on the left-hand side of load by multiplying K of T1 to the right-hand side of the equation. We can then come down here and look at this equation. We can set the values that we have in this equation equal to values that we already know. So K is equal to 0.01, the activation energy is 10,000, R is 2, T1 is 300, and T2 is unknown. Now for the equilibrium constant, Ke, Ke is equal to 10. The delta H of reaction is 6,000 over R, which is 2 as well. And then T1 in this case at equilibrium is 450 Kelvin. And we'll be plugging both of these equations into polymath. The last equation we need for polymath is the mole balance for the PFR, which is dx over dv equal to negative Ra over Fa naught. Now that we're in polymath, we plug in our 2 differential equations, which are here at the bottom, and we plug in our 9 auxiliary equations that are all at the top, and then click solve. Polymath then spits out these 2 graphs, which are needed for the solution of the problem. So this is the temperature versus volume graph of the reactor. So as the volume of the reactor increases around 2 decimeters cubed, it's at a max temperature of about 464 or so, and then after that it begins to drop off, where it levels out at around 454 Kelvin. And then below that is the conversion versus reactor volume, where the volume steadily increases as the conversion factor increases as our volume increases. It increases quickly at the beginning and then starts to slowly level off towards the end as the volume reaches 10 decimeters cubed. Thanks for watching.